How can we show the power of recursive error? Because later, after we solve the problem by recursion, you will see without using recursion, it is almost impossible. Yeah, I cannot. Yeah, I myself, I cannot solve it without recursion. Yeah, but I don't know if some other smart problem solver can do it. Yeah, it's that could happen. Yeah, but that would be extremely hard to find an iterative solution. Yeah. All right, so let's look at the problem first. Yeah. Our computing problem number 7, Tower of Hanoi. I think you did this before, yeah, because still in CS3250, yeah, we solved this one, yeah, because I used the material from my notes when I taught CS3250. Yeah, it is in our textbook, the Tower of Hanoi. You can find, the problem in our textbook. Yeah, but the solution, so I need to use some material from my CS3250 notes. Yeah, here. All right. Yeah. For example, the diagrams. So I took the diagrams from that class. Yeah, and to show the idea, so here we just use 3 disks. Yeah, but our goal, we need to solve for n disks. Yeah, any positive number n disks. So much harder. 3 disks already not trivial, right? Yeah, I think you know the solution, but for kids, it may not be easy, right? For young kids, okay? Yeah. This one is a puzzle. Yeah. So for many young kids, they like to, work on this challenging puzzle. Yeah, it's a puzzle. Yeah. First, let's understand the rules, the basic rules. All right. Number 1, only 1 disk can be moved at a time. Yeah. You cannot move 2 disks, okay? 1 by 1. Yeah. So every time move 1 disk from one peg to another peg. Total, you only have 3 pegs. Peg 1, 2, 3. All right. So you can only move from one peg to another peg. All right. But it will be covered in another rule. The second rule, a disk cannot be placed on top of smaller disk. Yeah. When you move, you cannot place a larger disk on top of a smaller disk. That rule. You have to follow certain order. Okay? Because this rule will make the puzzle harder, a little harder. Otherwise, without this rule, the puzzle is very easy. Okay? You can move in arbitrary way without this rule. Yeah. So this rule is important. Yeah. Make it harder. You have to maintain certain rule when you move your disks. Okay. Number 2. Number 3, all disks must be stored on a peg except while being moved. Yeah. This number 3, that's what I mentioned at the early time, because you cannot place 1 disk on the table. Think about, you place 1 disk, you put it on the table, then it's much easier, right? Because you have a lot of spaces on the table, right? You can, when you have many disks, before you put it on the destination peg, you use the large space area on the table or on the ground even, okay? On the ground, that's the violation, because that would make the puzzle too easy and trivial, okay? Not challenging, okay? Yeah, for that reason, we need to eliminate. We do not allow this happen. That's our rule number 3. Yeah. Then to solve it, it's non-trivial. Okay. And yeah, so here for the 3-disc puzzle, for young kids, it's non-trivial. Yeah. For us, it's very simple. But our goal, we need to solve the n-disc problem. That's non-trivial. Okay. Our goal is for n-disc, but here, because it's hard to draw the general n-disc case here, right? Yeah. So here, the 3-disc case, just for some simple illustration here, okay? Yeah. Later, we need to treat it as n-disc case. Yeah. All right. Yeah. Yeah. So the reference from our textbook, yeah, section 2.4, yeah, here, yeah. All right, so the analysis. The question, how to solve the general problem with n disks? Yeah. If you want to solve it directly, then it's hard. Yeah. I think you can imagine n equals 10 case. Yeah. We do not require, n equals 100, 1,000, that kind of relatively big numbers. Let's just imagine n equals 10. How many people in the world can solve this puzzle with 10 disks? Right? Yeah. I cannot, yeah. Because I may need to spend the whole day to solve it. Okay. I may need to spend the whole day if I work on a 10-disc puzzle, Tower of Hanoi. I do not have that patience, okay, the whole day doing things like this. Yeah. All right. Yeah. So here, the point I like to convey here, it's non-trivial. That's my point. Yeah, it's non-trivial, Yeah. All right. Yeah, non-trivial. Yeah. So we have to find some smart solution for it. Otherwise, we cannot solve it. Yeah, that's the point I like to convey here. All right. Yeah. We just learned recursive thinking. So here we will use that. We will use the power of recursive thinking here to solve this non-trivial computing problem. That's the point. Okay. All right. So let's start. Yeah. We start with here, the strategy. When we start from simple cases. Now here, when n equals 1, n equals 2, trivial, right? Yeah, we can call these two cases trivial. Yeah, so I do not even need to show you how to solve, right? Yeah, everyone can see it clearly. Okay, so I do not need to show you how to solve these two simple cases. Okay. All right. Yeah, so here, after that, so here, we can comfortably assume we have these two solutions for n equals 1, n equals 2. We already have the solutions. Okay, yeah. So we can move to the next step. The thinking here. When we solve the problem of size 3, yeah, after 1 and 2, we need to move to 3, right? Yeah. So we increase the problem size, grow it larger and larger. Yeah. But when we work on problem of size 3, we can assume that we have already solved the problem of size 2. Okay. Nothing wrong here, right? Yeah. Yes, we have that solution. Why we cannot assume that, right? We have that solution in our pocket. Why we cannot assume that, right? If some people challenge us, we just take it out from our pocket. Here is the solution. All right. Yeah. So, yeah. So that's why we can make the assumption like this. Okay. All right. Then by recursion, yeah, there is a gap, right? There is a gap between solution of size 2 and the solution of size 3. Yeah. The recursion, we need to fix it by, some special recursion. Okay. All right. Yeah, so here for n equals 3, we need to do some work to fill the gap. All right, yeah. So it's non-trivial, yeah. And we need to do some work here. Yeah. So the work we need to do, yeah, we need to get some experience. Yeah. Otherwise, if we do not have any experience, we do not feel comfortable for the discussion. Yeah. So in our next slide, let's do some experiment. Moving 3 disks. Yeah. We will do some concrete step-by-step work to solve the 3-disk puzzle. All right. Yeah. So when we start, this is the original state. Okay. 3 pegs, 3-disk power, yeah, in natural order. Yeah, we can call it, the order is natural. Smaller disks on top of larger disks. This order. Okay. Yeah. All right. The first step, we move the top disk to peg 3. Yeah. This peg 1 to peg 3. That's legal, right? Yeah. So we follow all 3 rules. So this move is legal. Okay. So we can go to the next step. Then the middle disk, we can place it on peg number 2. That's also legal, right? Yeah. No violation on any of the 3 rules. Yeah. After that, moving disk 1 back to peg 2. Yeah, this time also legal, right? Yeah. Yeah. All right. Step number 4, then the bottom disk, this time, the bottom disk, we can move it from peg 1 to peg 3. Now here we treat peg 3 as our destination peg. Yeah. Because at the end, all 3 pegs must be moved to peg 3 following the natural order. Okay. Yeah. All right. So now the largest disk is on our destination peg. All right. Yeah. So here I use, P of 2, yeah, represent the problem of size 2. Yeah. Problem size 2, that's the 2-disk problem, right? 2-disk problem, we assume we have the solution. Here, you see that solution. Yeah. So here you can see we need to move the 2 disks on peg 2 to destination peg number 3. That's a size 2 problem, right? So here we need to solve a size 2 problem. Okay. All right. Then how to solve? Yeah. So we move the smallest disk from peg 2 to peg 1. Then the middle disk from peg 2 to peg 3. And the smallest disk, this time, the last time, move to the destination peg 3. That's the solution. So you can see after 7 moves, 7 steps, each step just 1 move. So the total after 7 moves, we can solve that 3-disk puzzle. That's our experience. That's our experiment. Okay, yeah. Because with this experience in our mind, then we feel comfortable to do the further discussion. Yeah. But our next level discussion, we should use the recursion view. Yeah. Here we may not use the recursion view, right? Yeah. Because the number of disks, 3, it's a relatively small size. So we do not need to use the recursion view. So we can handle. Yeah. But when the size becomes a little larger, think about n equals 10. Yeah. N equals 10 without using the recursion view. How can you handle? I cannot. Yeah. I have to use the recursion view. Then I can handle disk 10 case. Yeah. All right. Question. How do we generalize the solution to n disk? Divide and conquer and the recursion. Yeah. So that's what we learned from our computing problem number 6, the factorial problem. Problem size reduction. Here we will use that problem size reduction. Okay, yeah. So n disk problem, P of n, that's a n disk problem, right? Then we do size reduction. So we can assume we have the solution of n minus 1 disks. Assumption, all right? Recursion, yeah. Then there is a gap, right? We need to fix the gap. Fix the gap by recursion. Then we can solve it. That's simple. Yeah, think about that. Divide and conquer, recursion view, and we solve this relatively hard problem in some simple way. Okay, yeah. So let's see the details for this part. Yeah. Without using recursion, it is very hard to solve the general case. So, yeah. Because when n equals 10, it's hard. Okay, yeah. All right. So here you can see, yeah, recursion method, we use problem size reduction. Okay, yeah. All right, yeah. So that's the simple idea. Yeah. Still, here we use the size 1 reduction case. Later, we will learn it's not necessary every time you reduce the problem size by 1. Yeah. Sometimes we can reduce more, yeah, more than 1. Okay, yeah. All right. All right, so here, let's look at the general discussion. Yeah. Yeah. Here we still, here, although you see 3 disk, I still use the diagram of 3 disk puzzle, yeah, because it's hard for me to draw n disk picture. Yeah, hard for me. Okay, so I still use the 3 disk pictures, but we can treat it as, we can imagine there are n disks here. Yeah, all right. So this stack we think, so we treat it as a n disk stack here. Okay, all right. Then, yeah, 3 pegs, we give them 3 different names, because later, when we write the pseudocode of implementation function, recursive function, we need to use these 3 pegs as the variables, okay, as the parameters. Yeah. So from peg, temp peg, the middle one, temporary, so temp, TMP peg, and the destination, to peg, okay, from to, and the temporary. Yeah. All right, 3 pegs. Yeah. All right. So then we use the problem size reduction way, recursion way. All right, yeah. Here, in order to solve problem of size n here, then we need to solve a problem of size n minus 1. And we can assume we have the solution. Okay, we have the solution. So that means we can move the n minus 1, top n minus 1 disks from first peg to the second peg. Okay, that's the solution. Okay, that's the P of n minus 1 solution. Okay, all right. After that, fill in the gap. We need to fill the gap. Okay, after that, yeah, here, this is P of n. Okay, fill the gap. All right. After, so I need to do after that. Here, let me just show you. We move the bottom disk to the destination peg, 2 peg, right? One move. Okay. After that, can we do another P of n minus 1 solution from temporary peg to 2 peg? Just another solution. Yeah. But with 2 different pegs. Yeah. And we know the solution essentially the same, right? Essentially the same as the first time we run the solution. Yeah. The only difference, just the starting peg and the destination peg are different. Yeah. Other than that, the moves you make, order, pretty much the same. Yeah. All right. So then we solve the whole problem. We solve that, P of n, the whole problem. Okay. All right. After that, here you can see the general solution when we use the recurrence view. So simple. So simple. Okay. Yeah. Then our implementation is also very simple. Yeah. So based on this view, our implementation is very simple. So my next slide, I show you the pseudocode of the implementation. Okay. Yeah. Here, move disks function. Okay. Yeah. So we recursive function. Here we have 4 parameters. The first one, the number of disk, the size number, okay, integer size number. Okay, all right. Then 3 pegs, yeah, from peg, 2 peg, destination, next one, and the middle temporary, we put it as the 4th parameter. Okay, yeah. So 1, 2, 3, peg one number 1, 2, 3. All right, yeah. All right. Then in now the body of the recursive function, yeah, recurrence function, if n greater than 0. Yeah. If n equals 0, so you can print out a message. Right? So there is no disk, things like that. Yeah. Here we just work on the main part. Yeah. When n num, yeah, when num, the problem size is a positive integer, then we do these steps. The first step, recursive function call on size 1 reduction problem, num minus 1. But we need to change the peg numbers. From the destination is the temporary one. This, yeah. The destination peg, we make temp peg as the destination and 2 peg as the temporary one. Okay, yeah. So just a recursive function call. All right. After that, fill in the gap. Yeah, You need to do something after you complete that solution. P of n minus 1 solution. Okay, after you complete that. So the gap part you need to put, because you move the bottom disk, right? When you move the bottom disk, you need to show people you are doing the work. Okay, you are doing the moving work. So you print out this message. Here I use C++ because that class is C++, right? Here, this one I also borrow from CS3250 because that class is C++. Okay, so I use the C++ way. C out, then the message part, move a disk from peg number, that you print out that the variable, the parameter value. After that, to peg destination, to peg, and you finish that message. But after that, you need to move the n-1 disks back to the destination peg. So you need to call the recursive function another one for non-1 disks. But this time you just change the peg numbers temp from temp, destination to, and the temporary you use from peg as the temporary. All right, so here you can see for such a non-trivial puzzle problem, we can solve the general case with these lines, very short function implementation. But the problem is non-trivial. It could be very complicated, but with this solution, so easy. That's the power of recursion. Okay, all right, so let me stop right here, because